In this video, we're going to take a look at section 7.1 on estimating a population proportion. So a proportion is a concept that we haven't identified with such a term. I would say that things we have looked at have really been related to this concept, but we haven't identified it as such. And I also don't think we've encountered a scenario in this course yet where we are looking at proportions from a sample and trying to use that to determine the proportion from a population, right? So, and that's kind of the distinction that we need to make in this section. So a proportion is not much different than like what we were doing with the binomial distribution in chapter 5. For that, we would want to know the probability of a success on any one trial, and a way that you could calculate that probability is using what we learned in chapter 4, which is how many ways can a thing happen divided by the total number of possibilities. And that gives you, in essence, a proportion, right? The proportion of ways that a thing can occur out of all the possibilities of what could happen when you run that trial. So in essence, a probability calculation like that is kind of a proportion. It is a proportion. Maybe I shouldn't use the word kind of. But we've never identified it with that particular kind of language. The other thing is with a binomial distribution, we are working with a population, right? We know all the possible outcomes. And so when we calculate a proportion in that case, we're getting a population proportion. And that will no longer be the case as we move into the problems that we're going to see here in chapter 7. And so we have to make this distinction between a proportion that we're getting from a sample and a proportion from a population, which we won't know. We're going to try to use the sample proportion to help us understand the population proportion. So a sample proportion is a ratio of the number in a sample that fit a given description over the total number in the sample. So let's say we have a sample of ACT scores. Right, so we've collected a sample of ACT scores from a group of students. Right, so we don't have the entire population, but we have a sample of ACT scores. And maybe we're interested in knowing what portion of students score over 20 on the ACT. So we could collect that sample, and within the sample, we can actually count how many students scored higher than 20 on the ACT, and then divide that by the total number of ACT scores that we have in our sample. And we get a proportion of students that scored greater than 20 in our sample. And we can use that to help us estimate the proportion of students in the population that score greater than 20. So that's what we're striving to do in section 7.1. And one way of estimating the proportion of the population is to just find the proportion in the sample and use that number as your estimate for the population proportion. But what we're hoping to do in 7.1 is something a little more sophisticated than that. We want to get a more sophisticated estimate. And we're going to be talking about that in just a minute, about the method that we're going to use to create a better estimate than just calculating the sample proportion. Okay, so the formula for a sample proportion is p hat. So that's how you, say, sorry, I have my writing tablet backwards, so it was not writing where I wanted it to. That's how you say this symbol here. It's the letter P with this kind of, it's also called like maybe a caret symbol, but it's read as p hat. P hat equals x over n, where x is the number in the sample that fits some description, and of course n is just the total number in the sample, right? It's your sample size. So it's a very simple calculation to calculate the proportion from your sample. Just count how many data values fit that given description, and then divide by the sample size. And now you have your sample proportion. And we can use that to try to better understand the population proportion, right? The population proportion is represented by the letter P. And it's the fraction of the population that fit that given description. But as is commonly the case, we won't have the data from the entire population. So we're just going to have to collect a sample, and we can measure that proportion from the sample and then use that to estimate the proportion of the entire population. All right. Now, the concept of using the sample proportion to estimate the population proportion is called a point estimate, which just means a single value estimate. So if you had to pick one number to best estimate the population proportion, it would be the sample proportion. That would be your best way of estimating the population proportion. And I'm saying the sample proportion, but I probably shouldn't use the word the or the there, because there are multiple different samples that we could get, right? And each one might have a different proportion. So I should say a sample proportion is the best way to estimate the population proportion. And so we would say that the sample proportion, a sample proportion, is the best point estimate. Since it's a single value, it's called a point estimate, and the sample proportion is the best point estimate for the population proportion. It's also true for the mean. The sample mean is the best point estimate for the population mean. And that's something we'll talk more about in the next section in 7.2. But that's what a point estimate is. It's a single value used to approximate a population parameter. In this case, that parameter is proportion. That's what we're looking at in 7.1. Now you might be wondering why, if we're going to be talking about the mean, which we've already talked about throughout this course, are we starting with proportion, which is a new concept that we haven't talked about. You would think if we're trying to explain a new concept, we should build on something that we've already been working with. The reason we're doing proportion first is because the tool that we're about to develop for estimating the population proportion, the more sophisticated tool, will be based on, I don't know if I want to say based on it, but utilizes the normal distribution, which we just talked about in chapter 6, right? And so and that's something we're familiar with, right? We just went over the normal distribution. We talked about finding, probabilities using the normal distribution, and the proportion works within the normal distribution. The distribution of the proportions does. The mean, however, doesn't. It's more complicated. We have to use a different distribution to do some calculations to estimate the population mean. And so because that's going to be different, we wanted to save that. We wanted the first section to be something based on the normal distribution, and then we will move on to the mean, which is based on a different distribution, and it's a little more complicated to do. So this is actually the simpler one to do first. That's why we're doing this one first. So here's an example of what you might see in the homework. This is still about point estimate. I'm kind of talking about the more sophisticated thing we're about to do, but jumping ahead of myself here. An important issue facing Americans is the large number of medical malpractice lawsuits and the expenses that they generate. In a study of 1,228 randomly selected medical malpractice lawsuits, it is found that 856 of them were later dropped or dismissed. Right, so that's just the background information and some numbers, some data to work with. The question is, what is the best point estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed? It's pretty common on some of the homework problems. I don't know if it's on every homework problem, but this will be like part A of a particular problem. So for the homework, you might have part A, what's the best point estimate? And then part B is going to be the more sophisticated thing that we're going to talk about in just a minute. So we're going to actually come back to this scenario after I introduced the next concept, and we'll do a part B to this situation. Excuse me. All right. So the best point estimate for the proportion is going to be the sample proportion, right? So this is the best point estimate for the population proportion. Now they didn't use the word population here, but that's what's being referenced. And the way we calculate that sample proportion is we take the number of cases that fit the description, which is cases that were dropped or dismissed, divided by the total number of cases that were in the sample. Right? The number of cases that were dropped or dismissed was 856, so that's the value for X. That's the number of successes. Again, not that it's a successful thing to have a lawsuit dropped or dismissed, but that's the thing we're doing the calculation on, so that is the thing we label a success. That's what we talked about with the binomial distribution, and there's some definite strong parallels here between the binomial distribution and calculating probabilities involving proportions. Right? Out of 1,228 randomly selected lawsuits, and that's going to be our value for n. And so we're going to get this fraction. Oh, I'm sorry, I wrote the equal sign like that. Let's try that again. We have 856 out of 1,228. And this might be the best way to leave the answer as the sample proportion, which is our best estimate for the population proportion, our best single value estimate. The thing we're about to learn how to do is to come up with a range of estimates, not just one number to estimate, but a range of possible values. That's what we're about to start working on. But if I have to pick just one number to estimate the population proportion, this would be the best number to estimate that. Now, if my stat lab says type your answer exactly, you want to leave it as a fraction. But if it says round to however many decimal places, that means you want to convert it to a decimal. So plug it in your calculator. 856 divided by 1228. And we get that the sample proportion as a decimal is 0.6971. I'm just going to go 4 decimal places, but I'm not sure what you might be asked to do on the homework. But about 70%, right, if we rounded that. About 70% of our sample were lawsuits that were dropped or dismissed. And that would be our best estimate for the proportion, the population proportion, right? So in our sample, 70% of the lawsuits were dropped or dismissed. So our best estimate for the population is that 70% of the lawsuits are dropped or dismissed. That would be our best estimate for that if we had to pick just one number to estimate it. All right, but we're going to be able to do more than that here in just a minute. So a confidence interval is a ranged estimate, meaning we're going to give a range of possible values for the population proportion. So it's a ranged estimate for the true value of a population parameter, in this case proportion. And this is what makes it even better, right? So you might say, big deal. You could take, why couldn't we take 70% and just kind of expand it a little bit and say, oh, it's probably between 67% and 73%, somewhere in there, and give it a range like that. But that's kind of arbitrary. What's great about the confidence interval is that we will, along with our estimate, provide a calculated built-in level of confidence for that estimate. Not one that we're going to make up just based on how we feel about it, but it's baked into the calculations. We will know exactly how confident we should be of our estimate based on our calculations that we do. So it's not something that you just guess at. It's in the calculations itself. So we'll say, here's your estimate, and here's how confident we are in this estimate, because that's what we calculated our confidence to be, right? It's a calculated confidence, not an emotional confidence, right? The how confident we are is called the confidence level. A confidence level represents the percent of times a confidence interval will actually contain the population parameter it is trying to estimate when a large number of confidence intervals are constructed. So a confidence level is really the percent of times we will get a good estimate that actually contains the value that we're trying to estimate. Right? So if we want to be 90% confident, that means we have to be able to do this calculation so that 90% of the intervals that we create will actually contain the population proportion. It also means that 10% of the intervals that we create will not contain the population proportion. They'll be off the mark, and they will be bad estimates. And we won't know which ones are which. That's the hard part, is we know the percentages on it. We know 90% of the time we're going to get a good estimate, 10% of the time we're going to get a bad estimate, but we don't know which ones are which is why we can't say for sure the estimate that we're calculating, whether it's right or wrong, but we can at least associate that percent with it. That, okay, here's an estimate for you. 90% of the times that I do these estimates, they give me a good estimate, and they actually contain the value that they're trying to estimate. They're actually, if I say it's between 67% and 73%, 90% of the time it will be. But 10% of the time, when I come up with these estimates, it will be wrong. It won't actually contain the value of the thing that we're actually trying to estimate. And we just have to kind of live with that uncertainty. So is this estimate you're giving me now one of the 90% good estimates, or is it one of the 10% bad estimates? There's no way to know. But we can feel 90% confident that the estimate we're creating is a good estimate. And that just reflects the percent of times that we expect our estimate to be good, to actually contain the number that it's trying to estimate. Right? So that's the concept behind the confidence interval is, here's an estimate, here's the percent of times this type of calculation produces good estimates. And then that's all we can say about it. And we don't know if this is one of the good ones or not, but 90% of the time, these are good. All right, so here's an example of what an answer will look like when you do a confidence interval. And this is just a made up answer from a non-existent situation. So there's some numbers thrown in here, but just to kind of give you a sense of what the final product looks like for a confidence interval. So we might have this thing that we call a 95% confidence interval. The 95% is the confidence level. So this estimate has a 95% confidence level, meaning that the method they use to create this estimate gives us a good estimate 95% of the time. Is this one of those 95% of the time? I don't know. This might be one of the 5% bad estimates. There's no way to know that, right? But because the process produces a good estimate 95% of the time, we can feel 95% confident that in this estimate that we've just created. And the estimate is that the population proportion, that's P, is between 0.677 and 0.723. Right? That's the estimate, that it's somewhere between those two values. And we're 95% confident that it is. So the way you should interpret that result, one way to interpret it, so this is not the only way to state it, but the thing, and especially as we move into chapter 8 and 9 and 10, we're going to be looking at some other things where we have to draw conclusions. And there's a script that you're supposed to use. And this is kind of what we're getting here, is a script for how to interpret the confidence interval. And it's not the only way of interpreting it. It's not the only wording that's valid. But if you deviate from that script, you might say things that you might think are the same thing. You might think, oh, this is equivalent to this, but it really doesn't mean the same thing. There's a lot of subtlety here with, statistics. And so I would really recommend, if you're asked to interpret a confidence interval, that you try to stick to the script that we provide. I'm willing to accept alternate answers, but if you word it differently, I'm going to think very carefully about the way you're wording it. And if it doesn't quite say the same thing, then it'll be wrong, right? And you might think it's saying the same thing, but there might be some little detail that the wording that you use might, actually not be exactly the same as what's stated in the script. I hope what I just said made sense, but it's dangerous to freestyle on these, interpretations or these conclusions, because what you think you're saying might not actually be what you're actually saying. Or I don't know if that's really the right way to say it either, but the wording you're using, you might think is equivalent to the original script, but maybe it's not. And it might be hard to catch that. It's hard for me to catch it sometimes. Sometimes I've had students word things and I'm like, I have to sit there and really think about it. Like, what does this really mean? And you have to kind of look for like fringe cases. Like, I don't know. You have to really kind of, analyze it pretty closely to know exactly what it's trying to convey and to make sure it's conveying the same thing that the script is conveying. All right, so here's a good interpretation of a confidence interval. We are 95% confident that the interval from 0.677 to 0.723 actually does contain the true value of the population proportion P. All right. The 95% is our level of confidence. What would be absolutely wrong to say, and again, students actually will kind of think of these two statements as saying the same thing, but it's not. It would be wrong to say there's a 95% chance that the true population proportion is between 0.677 and 0.723. That is incorrect, because we don't know what the true population proportion is, but it's a fixed number. Whatever that number is, it's fixed. It doesn't change. So it's either between these two numbers or it's not. It's not a chance. It's not like maybe, maybe this time it's 90, like maybe, I don't know how to say this. 95% of the time it's between these two numbers, but 5% of the time it's not. That's what you're saying there. If you say there's a 95% chance that the number's between these two, you're saying that the number changes, and 95% of the time it's between 0.677 and 0.723, and 5% of the time it's not between those two numbers. And that is incorrect. It's either between the two numbers or it's not. It's a yes or no. It's not 95% of the time it is, and 5% of the time it's not. So you don't want to say the second thing. And be careful, because on the test, I have put a question in the past where I say, here's a confidence interval result. How do I interpret this? And you can bet both of these will be in the multiple choice options, right? And a lot of students will pick that second one, and they'll say there's a 95% chance it's between these two numbers. And that's just the worst one that you could pick, right? 95% confidence means that if we were to select many different samples, because each time you want to make a confidence interval, you have to get a new sample to do that. So if I want to make 2 confidence intervals from the same population, I have to get 2 different samples to do that, right? So if we were to collect different samples of the same size and construct the corresponding confidence intervals, about 95% will actually contain the value of the population proportion P, and about 5% of them will not. So again, the 95% has to do with the percent of our confidence intervals that should be good estimates of the population proportion. Right? Okay. So that's how you interpret it. All right. Now, in order to even be allowed to construct a confidence interval to estimate a population proportion, there are some requirements that have to be met. The sample that you're collecting has to be a simple random sample. The conditions for the binomial probability distribution must be satisfied. So that goes back to chapter 5. But remember, there was 4 conditions in order for us to have a binomial distribution. So again, that's why, again, proportions and binomial distributions very, very closely related. There is a fixed number of trials. So again, the sample size has to be the same every time. The trials are independent. There are 2 categories of outcomes, so either success or failure, right? And the probabilities remain constant for each trial, right? So this probability of a success on any one trial can't change as we continue to collect, things for our sample. Okay. And then the third requirement is that once you have your sample, there needs to be at least 5 successes in that sample and at least 5 failures in the sample. Now, some students will look at that and say, so you mean there has to be 10? The sample size needs to be 10, because that way you get 5 and 5. No, that's not what that says. In fact, being able to achieve this with only 10 would be unlikely, and would be like, that's the best case scenario, that if you happen to get 5 successes and 5 failures in your sample size of 10, that would be the lowest number that you could achieve this with, but it's also unlikely to happen. So for example, let's say I'm collecting 10 things from my population. My sample size is 10. And let's say of those 10, 9 of them are successes. If I could spell. Which means 1 of them is a failure. So if I say, let's have a sample size of 10, and I collect my sample, and I get 9 successes and 1 failure, I have not met the third requirement. I've met the 5 successes part of that, but I haven't yet achieved 5 failures. So I need to collect more for my sample until the number of failures also reaches 5. And it could be a while before that happens, especially if this is the ratio that you should expect. So you might have to get a sample size of like 50 before you finally hit that 5th failure, right? You have to have both of these be true. There has to be at least 5 successes and also at least 5 failures, and that will often require more than 10 in your sample to achieve, right? Okay. Here's the formula for constructing a confidence interval, right? So not too scary looking, right? P hat, we've already talked about. That's your sample proportion. Sample proportion, right? Minus E, which is something we haven't talked about yet. This is the margin of error, which you probably have heard of before. Like whenever you see survey results, they like to give a margin of error, which actually these proportion problems are highly related to surveys, right? Because when you do surveys, you're getting proportions. What proportion of people favor this rule? What proportion of people favor this candidate for president? It's proportions. And those survey results have a margin of error that they calculate. And so this, we're going to be calculating. Now, there's different ways of calculating a margin of error. I think I remember reading this in the textbook at one point. And the way we are choosing to calculate our margin of error is actually the simplest way it can be done. So, when we get through this, all the details here, you might say, oh man, that's so complicated. It's actually the easiest way this kind of thing can be done. And there are more sophisticated ways of doing these kind of calculations, but we're trying to stick with the easiest path possible, but it's still pretty complicated, right? Now, when you take the sample proportion minus your margin of error, which I'm going to talk about how to calculate in just a second, that's going to give you your lower estimate for your confidence interval. Right, so you're going to have an upper estimate and a lower estimate. You calculate the lower estimate by taking the sample proportion minus the margin of error that you calculate. You take the sample proportion plus the margin of error to get your upper estimate for the confidence interval. And once you have the lower and upper estimate, your confidence interval becomes between those two numbers, right? So you're estimating that the population proportion will be between either the lower estimate, I don't know why I said either, the population proportion will be between the lower estimate and the upper estimate. That's going to become your interval estimate for the population proportion. And so since that's the thing we're estimating, that's what goes in the middle, right? This is the population proportion. And we're saying it's going to be between these two values. And that's what our confidence interval is going to suggest. And we will have a confidence level that goes along with that suggestion to say, this is how confident we are that the population proportion is between these two numbers that we calculated. Right. Now, so that's the final product. This is how you get that final product. But in order to get the final product, you have to calculate a margin of error. There is a formula to do that. So I actually taught this in my class today, again, I was trying to record all these videos ahead of time before I actually got to them in my class. And it's caught up to me. So I'm kind of right neck and neck now. So like what I'm covering in class is what I'm also needing to record in order to keep up with, the pace of the course so that my at-home students can learn along with my in-class students at the same pace. So, and what I told them, and I think it's a good analogy, but I guess now, again, I don't have a lot of students actually coming to my face-to-face class. So I think I had like 4 students in class today. So this is a very small sample size. And I asked them, how many of you have seen the movie Inception? And it was 50-50. Half of them had, 2 of them did, 2 of them didn't. I don't know if that's reflective of the general population, using some statistical concepts that we've been talking about. But if you haven't seen the movie, I recommend it. It's kind of mind warping, but in order to explain why I'm bringing it up, I need to tell you the plot a little bit. I'm not going to give anything away, no spoilers or anything, but the concept of the movie is that people can enter other people's dreams. And so what they do, they hatch this plan they're trying to accomplish something, which I won't get into, but in order to make it work, they have to go inside of somebody's dream. And then once they're inside of one person's dream, they have to have somebody in the dream start dreaming, and then they go inside of that person's dream. So they are in a dream within a dream, which if you've seen The Princess Bride, that's a funny line in that movie too. It makes me think of that, dream within a dream. But they actually go even deeper than that. So then they go inside of another dream inside of that dream. So they're in a dream within a dream within a dream. Right. I kind of feel like calculating these confidence intervals is kind of like that. Now, the cool concept in Inception is that when they're ready to leave a person's dream, they need to be awakened with a jolt in the dream level above it, right? So whatever dream level they're in, if they want to wake up from that dream, they got to get jolted in the level above it to wake up into that level dream. It gets crazy. It gets kind of complicated, but it's a good movie. It's still fun to watch. And there's like really cool action sequences, right? And the name they give it in the movie is you have to give them a kick, right? That kind of jolts them awake. So you have to kick out of this dream level back into the higher level dream. and then kick out of that one. So ultimately in the movie, what they're planning to do is once they've done what they need to do in the dream within a dream within a dream, they want to kick all the way back out to reality, back to the waking world. So they kind of kick all the way back out. That's how these confidence intervals get constructed, right? So the level we're at now is like level 1. This is the level 1 dream that we're looking at right now. But we have to go one level deeper. We have to go into a dream within a dream, which is the margin of error, right? So we have to, go further into this, right? So find the margin of error. That's this formula here, right? So we have E, the margin of error, equals this thing, which is Z sub alpha divided by 2. And I'm sorry, the formatting I'm using here makes this a little bit oversized. I tried to shrink it down, but I couldn't make it any smaller. But usually when I write it, it's, this is a little smaller. But this thing is an alpha. It's a Greek letter. And we're going to talk about, I haven't told you what that is yet, but I will in just a minute. In the next dream level, right? We're not quite there yet. So, but it's Z sub alpha divided by 2. This is called the critical value, which we also haven't talked about yet, which will be the next dream level that we're going to talk about, right? Times the square root of p hat times q hat divided by n. Now, p hat we've already talked about. That's the sample proportion. Q hat, I was kind of disappointed with my class today. I shouldn't say that because if they end up watching it, I don't want them to feel bad. But I asked them, what do you think that's equal to? Because we've seen this already, right? Like I said, there's a lot of analogies here to binomial distributions. And if you think back to chapter 5, Q in chapter 5 was equal to 1 minus P. And that's exactly the same thing here. So maybe I shouldn't write it right here. Let me write it off to the side. All right, whoops. So we already know that. That's the sample proportion. Q hat is 1 minus P hat. So that's pretty easy to calculate. We don't need a whole separate dream level to discuss that. It's a pretty simple calculation. And P hat's the proportion of successes in your sample. That makes Q hat the proportion of failures in your sample. That's what that is. And you want to multiply those together, divide by n, which is again also something we've already talked about. That's the sample size, right? So that's how you get Q hat. But for the critical value, we got to dig deeper, right? There's more to explain there. We have to go down into the next level of dreams, right? And so we have to kind of, so how do I want to say this? We're going further in. I don't know. I can't think of a good way to say this. But we can't calculate this until we understand what this Z is. So let's focus in on that and talk about that. So as I said, this is the critical value. And you might say, oh, there's nothing here to, this dream is getting kind of boring, right? Because there's just nothing on the screen. But I'm going to draw it in instead of having it already typed there. So this value is from the normal distribution. It's a z-score. And so you're going to learn to associate the normal distribution with z-scores. They go hand in hand. So if you ever are asked to find a z, that will be from a normal distribution. And if you're asked to find a value from a normal distribution, it will often be a z-score. Now, we talked about z-scores in chapter 3. It's the same concept here. Z is measuring how many standard deviations away from the mean a particular data value is. It still kind of functions in the same way here. So if z is equal to 2, it means we're 2 standard deviations away from the mean. To calculate this z sub alpha divided by 2, we're going to try to draw the normal distribution. I feel bad because I draw it so horribly on these videos. But in class, I'm not quite as bad. I have the smartboard, but it's just a little bit easier to control how my drawing looks on the smartboard. And so in class, I feel like I do a pretty good job drawing these, but in the videos, it's pretty bad. What we're doing is we're taking this alpha divided by 2. And I'm going to tell you how to find that in just a second in the next dream level after this one. Which will be the last one. That's as low as we're going to have to go. Whatever this number is, this alpha divided by 2, that becomes the area in the right tail of the normal distribution and in the left tail. Right. And so what we're going to be looking for is the value associated with that area being in the left tail or in the right tail. And it turns out for z-scores, you can actually find either one. You'll get the same number either way, because for z-scores, 0 is in the middle. Right? As long as we're talking about z, the z-score of 0 is at the peak of the normal distribution. And so that symmetry means we get the same number either way. But most people calculate this one because the way we calculate this value, this is what we just learned in chapter 6, is using inverse norm. Right? So if you have the area and you want to calculate the data value associated with that area, you use inverse norm to do that. But for my calculator, and again, the newer interfaces on the newer TI-84s, they might let you customize which area, whether it's the area to the left, area to the right. I'm not sure what everybody's capabilities are, but I just know for my calculator, inverse norm needs the area to the left. So this one's just more convenient because this is already the area to the left, but that area is alpha divided by 2. Let me use a different color here. So this area is alpha divided by 2. This area here is also an alpha divided by 2. So they both have the same area, but this one, the area is already to the left, which is what I want for inverse norm. So that's what I'm going to type into inverse norm, whatever alpha divided by 2 is. Now in chapter 6, we talked about inverse norm actually needs 3 numbers. It needs the area to the left, it needs the mean, and it needs the standard deviation. But for z-scores, the mean is 0 and the standard deviation is 1. That's what's useful about z-scores. It standardizes that normal distribution for us by having the values as z-scores. And what's also useful about that is if it's standardized, you don't have to type in the 0 and the 1 for the mean and the standard deviation. Just the area suffices, and it automatically assumes those other numbers. If you don't type them in, it assumes 0 and 1 automatically. Again, on my calculator, but if you have a different calculator with a different interface, if it makes you type in the mean and the standard deviation, you want to use 0 and 1 for that. So we could also just do inverse norm. The alpha divided by 2 is our area to the left. Let's try that 2 again. And I'm sorry, my alphas kind of look like 2s. That's why I'm worried about this. These kind of look the same, but this is an alpha. It's flat. It's supposed to be flat. This is a 2, comma, 0, comma, 1. And either way, this gives you a z-score, right? So if your mean is 0 and your standard deviation is 1, when you're using inverse norm, you're actually getting a z value as a result. And that's what we're looking for here. Right, and so that's going to be our z sub alpha divided by 2. So the subscript is just indicating what the area is to the left of that number. Now, the z-score here should be positive, right? So this is the critical value is always positive. So you have to be careful because when you do this one, it's on the left tail. So inverse norm is actually going to come out negative. So you'll get negative some number here. You drop the negative sign for the critical value. You just take the number, ignore the negative sign. All right, so we're almost ready to actually do something with all of this. The last layer we need to dig down to is, what is alpha? I haven't told you what that is. So we need to, so think about like how this all connects back up to the top. We need to find alpha in order to get this z-score. We need that z-score in order to calculate the margin of error. We need this margin of error in order to calculate the confidence interval. Right? So you see how it kicks back out, right? It starts at the very lowest level. The dream within a dream within a dream is finding alpha. Once you find that, you kick out from that dream and you use that to find z, the z-score, the critical value. And then once you find the critical value with alpha, you can kick out from that to up to the next layer, which is the margin of error. And once you calculate the margin of error, you kick back out to the confidence interval, this formula here. Okay, so alpha is just 1 minus the confidence level. It's very simple. This dream level, there's not much else to say. It's 1 minus the confidence level, which will be given to you. You might say, well, how do I know what the confidence level is? It will be given to you. Now, if you're applying these concepts on your own, like if you happen to be wanting to apply some statistics for just your own personal use or whatever, you would get to decide your confidence level. You can pick whatever you want. The standard ones would be like 90%, 95%, 99%. Those are your most common ones. But in this class, for these problems, it's chosen for you. So you will be told what confidence level you need to have. Now, a good question to ask is, well, why not 100%, right? Why wouldn't you just go for 100% confidence so that you know you're absolutely not wrong? Well, The thing about these confidence levels is the more confident you want to be, the wider your net has to be. You have to cast a wider net in order to be more confident that your estimate contains the actual value. So it might seem kind of backwards, but the less confident we are, the more narrow our estimate can be. So if I'm willing to just be 90% confident, I'll get a small window as an estimate, which is nice, but I'm less confident about it. If I want to be 99% confident, I get a bigger window for my estimate. So I'm more confident that I'm actually containing the value that I'm trying to estimate, but it's a wider estimate. So in that way, it might not be as useful. If you want to be 100% confident, you got to go from like 0 to 100%, right? Your estimate's just going to be every possible number that it could possibly be, which is a useless estimate. So you can't be 100% confident because the estimate you get will just be so wide that it encompasses all possible values and makes it useless, right? It would just be a useless estimate. So unfortunately, you can't be 100% confident. And the math just wouldn't work out because what would happen is I don't know, what would it be? If you wanted to be 100% confident, alpha would be 0. Putting 0 in the tails means that the z-score would be infinite. So your margin of error would be infinite, and so you'd have negative infinity to positive infinity for your estimate, right? I mean, the math would force that to be your estimate. I thought it might just be from 0 to 1, but it actually would just come out as negative infinity to positive infinity, which would be useless, right? Okay, so that's how you find alpha. So if you have a 99% confidence level, that means you would put 0.99 as your confidence level in this formula. And in that case, alpha would equal 0.01. Right? And then you would take that alpha, divide it by 2, because half of it has to go in the left tail and half of it has to go in the right tail. So remember, if we're 99% confident, that means 99% of our confidence intervals will actually contain the thing we're trying to estimate. 99% of them will be good estimates, which means 1% of them will be bad. So alpha is the percent of bad estimates that you're going to get from this process, right? And they could be bad because they're too low, or they could be bad because they're too high. So 1% altogether will be bad estimates, but half of them will be bad because the estimates are too low, too far into the left tail. Half of them will be bad because the estimates are too high. They're too far into the right tail. So that's why we're having to take the alpha and divide it in 2, right? Half of our bad estimates will be here because the estimates are too low. Half will be in the right tail because they're too high, right? And then once you have that number, so if alpha is 0.01, you divide that by 2, right? So you have 0.01 divided by 2, which gives you 0.005. That's going to be the area in the left tail. You plug that into inverse norm, you get a z-score out of that. Once you have that z-score, you can plug it in here along with your sample information, get the margin of error. Once you have the margin of error, you're calculating your confidence interval, right? So that's the process. It is multi-step. There's a lot of parts to it. And like I said, it kind of, it's nested like a dream within a dream within a dream, right? So you have to get this thing first before you can get this thing. And then once you have that thing, you can get this thing. And then once you get that thing, you can get the answer, right? So let's practice. And I know it seems complicated, but I promise you, with a little bit of practice, I really don't think it takes much for students to really kind of catch on to the whole structure of the problem. So once you do 3 or 4 of these, I would say, you'll probably have a pretty good feel for how that whole process works, and it won't seem as bad. So it looks bad at first. It's horrible to even try to explain, right? Because that's a hard thing to explain. I was really bad at it. I might still be bad at it. I don't know. That's up to you to decide, I guess. But the first couple of years I taught this stuff, and I'm not a very organized person, so my work is all over the place, and I had trouble explaining how to get all the information and put it together to get the answer. So it's taken me a while to kind of think of a good way of explaining it. And I think Inception actually is a really great analogy there. So back to the lawsuit example we talked about earlier, right? Same numbers. We have 1,228 randomly selected lawsuits, and 856 of them were later dropped or dismissed. We want to calculate a 99% confidence estimate of the proportion of medical malpractice lawsuits that are dropped or dismissed. So this would be like the part B of the problem, right? And this is a common format for the homework. Part A, what's the point estimate? Part B, construct this confidence interval. All right, so I like to kind of start from the top, from the first dream level, right? So let's scroll down a little bit more, which is, here's my answer. P hat minus the margin of error will give me that lower estimate. The thing I'm estimating goes in the middle, and then P hat plus the margin of error will give me the upper estimate. So I usually start off with, what do I already know? If I already know something here, I'll just go ahead and plug it into my answer, and I'm already that much closer to having the right answer, right? And we already know P hat, right? We know P hat is 856 over 1,288. 88 or 28? Now I'm questioning myself. Whoops, hit the wrong button. I guess that actually would work. It showed me what the number was. 1,228. See, that's how you're going to get yourself in trouble if you're not careful with those numbers, right? So 1,228, right? That's P hat minus the margin of error, which I don't know yet. So I'm going to have to leave that blank for right now, which is why I left a little bit extra space here. And I'm going to skip over here. The thing I'm estimating goes in the middle. P hat, again, is 856 over 1,228 plus whatever that same margin of error is, which I don't know yet. So I have to pause this, right? I have to put this on timeout because I don't have all the information I need to get my answer yet. And I need to go searching for E, right? So I'm going to, kind of divide this off. I'll come back to this later once I have the information I need. What I need to know is E. What does E equal to? The formula, I pushed the button to erase, and that's why it didn't write for me. Z sub alpha divided by 2 times the square root of P hat Q hat over N. And most of these I either know or I can figure out pretty quickly. The one I really have to spend more time looking into is the Z sub alpha divided by 2. But let's go ahead and, again, like we did over here, let's plug in what we know, and then whatever we still have to find out, we'll go find it, right? So I'm going to scroll over this way because I'll need some more room. So again, P hat we already know. Now you might be wondering, why am I using the fraction? Maybe you wouldn't want to use the fraction here. But if you use the decimal, the concern I have with that is, for part A, and this throws people off, right? Find the best point estimate, round it to 2 decimal places. Okay, that's fine. But then for part B, you don't want to have the rounded off number because you're taking that point estimate and you're doing a further calculation with it. And so you don't want to round it off, because if you use a rounded number to do more calculations, your calculations are going to be off. So you want to actually go back to the original number that's not rounded. And if you're going to do decimals, you got a lot of decimal places to write. So I feel like it's easier to keep this number exact if I just have it in fraction form. And then once I get to the end, then I'll dump it into my calculator to get a decimal. But I want it to be exact as I'm typing it into my calculator. And the best way to guarantee it'll be exact is to have it as a fraction. Not only that, so it's going to be, easier, less writing, more exact. There's actually kind of a shortcut you can do with this if you have it as a fraction that I'll show you when we get to that part of the problem. So I'm going to put that in parentheses, right? So that's the P hat value. Then the denominator is N, which is also 1,228, right? So that's N, and I'm going to put that here. And we have a square root going around that whole thing. So what I don't know is Q hat, but I don't need to go to a whole nother dream level to figure that out, right? Q hat is just going to be 1 minus P hat. I'll just kind of figure it out real quick right now. Right? It's going to be 1 minus the 856 over 1,228. And so you can plug that into your calculator, but you want the answer as a fraction here as well. So if your calculator can produce the answer as a fraction, then go ahead and do it that way. If not, maybe you want to take the time to do this by hand. You got to get a common denominator. So think of this as 1 over 1. The common denominator is 1228. I multiply that to the top and bottom. That gives me a common denominator. And now that I have the same denominator, I can subtract these. So it'll be 1228 minus 856, which is 372. So I get 372 over 1228. Don't bother reducing it. It actually works out better having all these denominators be the same. So this is Q hat right here. So that's what I'm going to plug in for Q hat. And so here we're going to have 372 over 1228. So all I have left now is to find z, which I don't know. I don't know what z is equal to. So we have to take a timeout again on this calculation. So I'm going to leave some space there. And I don't know where to go here. I guess maybe we'll go off to the side over here. So maybe in this space over here. So on some new space on your paper, set aside a little area for calculating z sub alpha divided by 2. Now to calculate that, we have to go to the very last dream layer, whatever you want to call it, to find alpha. But it's a quick calculation. Alpha is 1 minus the confidence level, which in this problem was 99%. That was given to us. We don't get to pick that, right? The confidence level is right here in the problem. It's 99%, which means I'll put 0.99 here as my confidence level. Alpha is 1 minus that. Right? So alpha for this problem is going to be 0.01. Right? That's our value for alpha. To find the critical value based on that alpha, I want to take that alpha, divide it by 2. So let me write that a little bit better because my 2's look like alphas, right? So it's going to be 0.01 divided by 2, which as I already did this calculation, is 0.005. I want to put that amount in as the area in the left tail and the right tail of the normal distribution. All right, so I'm going to draw a normal distribution here. All right, so let me say this, guy. I really like this inception analogy. We found alpha. That's the deepest level that we've gone to, right? Alpha. We found alpha by just doing that quick calculation. So we kick out of that level back to the critical value level, right? So now we need to find the critical value using that information that we just got from the lowest dream level that we're going to, right? It's 0.005. That's the area that I want to have in the left tail and in the right tail of the normal distribution. I'm really bad at drawing arrows. All right, so I have I don't even want to put it there actually. So here and here we have, let me use a different color. We have an area of 0.005 and an area of 0.005. All right. We want to find the value, the z-score associated with that area. So we're going to use inverse norm to do that. And we're going to type in the area to the left of this particular value, which is 0.005. Right? It's the alpha divided by 2. So I use my calculator. I do inverse norm, 0.005. And I find my calculator tells me negative 2.57. And here I might be rounding too much. And this is sort of a do as I say, not as I do example. I'm going to go ahead and round this because I'm used to rounding z-scores to like 2 or 3 decimal places. That's just kind of my habit. And so this is going to round to 2.576. But if you're doing that and you're not getting the right answer, it could be because we're rounding this too much. So when you're doing the homework, you might not want to round it quite this much. You might want to keep all the decimal places just to be, that's the safest thing to do, is just keep all the decimal places. And there's a bunch of them. Unfortunately, I'm setting a bad example here. But now my z-score, my critical value, this is my z-score, but for the critical value, we're going to use that number, but we're going to drop the negative sign. 2.576. That's my critical value. So drop the negative sign. That's the critical value that you want to use. So now we're done with that dream layer, that dream level, whatever you want to call it. So we can kick out of that one now. We're done with it. So kick out back to the next, up to the next layer that we were working on, which is the margin of error. So now I know what z is equal to. Let's take that value of z and plug it into the formula. And now that we know what z is equal to, we can find the margin of error. Right? So you see how we're kicking out from the lowest level, right? Alpha was the lowest level. We find that, we kick out to the next level, which is finding the critical value. Once we find that, we can kick out to the margin of error level, and we can find that now that we know what z is equal to. So I don't know, maybe I'm wearing that analogy a little too thin. So I won't keep using that analogy in the next examples that we do. So, but the z-score is 2.576, right? And I'm sorry, that decimal place is hard to see. Let me make that a little bigger. 2.57. Oh, Now it doesn't want to write for me. 576. Multiply to that square root. Now the shortcut here that we can use that I promised you earlier, if you keep these as fractions, and this is some algebra, so again, I love pointing out, like, why is college algebra a prerequisite for this course? Because there are some situations where algebra is needed or useful, and this is one of the cases where it's useful. You can leave it like this, but that's a big mess. I wasn't going to say a bad word there. I was about to say that sure is a big mess, but then I changed my mind about saying sure. That is a big mess to have to type into your calculator, right? So we can make this easier to type into our calculator using a little bit of algebra. It turns out I'm not going to go into the details of the algebra that makes this work, but if these three denominators are all the same, even if they're not the same, they end up on the same level. They all three end up as the denominator of one big fraction. And because they're the same, we can just write them together using exponents. So if they were all different, you could still do this maneuver, but then it wouldn't really help that much because you'd still have a bunch of numbers in the denominator. But since they're all the same, exponents can simplify this for us. So we'll have E equals the 2.576, right? That's the critical value, times the square root. The 856 stays on top, times the 372 also stays on top. And then these three all end up in the denominator, multiplied together, which means I can write it as 1,228 to the third power. And that's just going to be a lot easier to type into my calculator. So let's go ahead and type this into our calculator and get the margin of error. Right, it's going to be 2.576 times the square root of 856 times 372 divided by 1228 raised to the third power. And I come up with 0.03378. I'm just going to, again, bad form on my part. I probably should keep more decimal places than that. But I think that's going to be enough to get a good answer out of this situation. That's a margin of error, which is about 3%, right? So again, if you think about on surveys, when they show these surveys on the news, they'll say, oh, this candidate is favored by 57% of the populace. This candidate is favored by 43% or something like that. And then at the bottom, they'll say margin of error, 3%. That means it could be off 3% either way. It could be 3% higher than what they're reporting, or it could be as low as 3% below what they're reporting, right? So that's the range of possible values. So they're giving you the point estimate, right? If 54% of people prefer this candidate, that's the point estimate. That's the single value estimate. The margin of error gives you the range of possible values, right? So if it's a 3% margin of error, it could go up to as high as 57% or as low as 51% for that candidate, right? If 54% is the estimate, the point estimate, it can go 3% below or above that. It can go as much as that, right? It doesn't go exactly that amount, but anywhere in between 51% and 57% would be possible, right? And so that's how they get margin of errors on those surveys that you see on the news, right? So now we have that margin of error, we can complete our confidence interval. I don't know if there's a way for me. I guess if I zoom out, that might help, right? So let's zoom out a little bit. Here's my margin of error. I'm done with this dream level now. So I kick out of this dream level and I'm back to my original dream where I can now plug in the margin of error that I just found, right? And so here we're going to have 0.03378. And here we'll have the same thing, 0.03378. So we get the lower estimate by subtracting the margin of error from that point estimate. And we get the upper estimate by adding the margin of error to that point estimate. And this gives us the range of possible values for the population proportion. So now I'm going to take that fraction and plug it into my calculator. 856 divided by 1228 minus that margin of error. And I get 0.6634 as the lower estimate. And then 856 divided by 1228 plus the margin of error, 0.03377976679. I'll just type the whole thing in since it's on my calculator. And I get 0.7308. All right, and there we have it. This is our 99% confidence interval estimate for the actual proportion of lawsuits that are dropped or dismissed, medical lawsuits that are dropped or dismissed. So we can say that we're 99% confident that somewhere between 66% and 73% of all medical malpractice lawsuits are dropped or dismissed. Right? That's for the entire population. And we're 99% confident in that estimate. Now, the question, the last part says, does it appear that the majority of such suits are dropped or dismissed? Now, that question, there's a lot of hidden meaning in that question. I don't know if meaning's the right word there, but I think there's some, people will take some of these words for granted, but there's actually very concrete definitions for what these words mean. And one of those words is majority. So when we use the word majority, a lot of people, I think, consider that to mean, well, a lot. If it's a majority, it means a lot of people think that. But majority is actually more explicitly defined than that. Majority means more than 50%. That's the actual definition of majority. So, if somebody is running for office and they only get like 40% of the vote, maybe that's the most out of everybody, but that's not a majority, right? 40% would not be a majority. In that case, it's called a plurality. So if you have like 3 candidates running and one gets 40%, one gets 30%, and the other one gets 30%, right? That's 100% altogether. The 40% candidate wins, but they didn't win with a majority, right? It wasn't more than 50%, right? They won with a plurality of the votes. So it's called a plurality in that case, right? So when they say majority, they're not asking you, do you think that's a lot? Do you think this is a lot of cases that get dropped? They're specifically asking, does it appear that more than 50% of such suits are dropped or dismissed? So it's very explicit there, right? So majority, I'm trying to think of a good place to write it, means more than 50%. That's literally what that means. And you have to think of it that way to answer this question correctly. Now, based on our estimate, the answer is yes. More than 50% of cases do appear to be dropped or dismissed because our estimate is clearly above the 50% mark, right? So if you think of this on a real number line, if I could draw a horizontal line, well, that's pretty bad, but we'll just go with it, right? Let's say 50% is right here. Right? Our confidence interval is above that, right? Our confidence interval goes from 66% up to 73%. So this is what we estimate as the percent of lawsuits that are dropped or dismissed. This range right here. We think it's somewhere between those two numbers. Somewhere between 66% and 73%. In fact, we are 99% confident that it's somewhere between those two numbers, which is clearly above 50%. So even worst case scenario, the lowest that we would consider the percent to be is 66%. And that's still a majority. So if your entire confidence interval is above that 50% mark, then yes, you can be confident that it's a majority. It's a majority in this case. So we would say yes, a majority of lawsuits seem to be dropped. And we can say that with 99% confidence, right? I would almost say 100%, because even if this is a bad estimate, it's still so far above 50% that the actual value of P is very unlikely to actually dip below 50%. It's even if it's, below this, it would still only be like maybe, it's not going to be far off, right? It might be 60%, 65%. So I would say we're almost, I mean, again, this is just me. This is not how you should answer the question technically, but I'm 100% confident it's more than 50% because even if this is a bad estimate, it should still be close. And so it seems pretty clear that P is going to be more than 50%. Now, that's how you would answer it in this case. But I do want to talk hypothetically here because, you might have a different situation on the homework than what we just encountered here. So if let's say our confidence interval was between 40% and 45%, right? 0.4 and 0.45. Let's say that was our answer. Then we could say, no, it does not appear, right? So 50% would be right here. Our confidence interval places the actual value of P between 0.4 and 0.45, somewhere in here, which is clearly below the 50% mark. So we could answer confidently, in this case, that no, it does not appear that a majority of cases are dropped because our estimate places that value below 50%. So we can be confident in this case answering no. We would say, no, this is not a majority. Right? No, this is definitely less than 50%, right? Our estimate seems to indicate that it's definitely less than 50%. So if your confidence interval is completely above 50%, you can answer conclusively that yes, it's a majority. It's clearly above 50%. If your confidence interval is all completely below 50%, you can answer definitively, no, it's not a majority. But another possible thing that can happen is, what if your confidence interval is between like 0.48 and 0.53? If that happens, this is inconclusive, right? Because 50% would be right here, and your estimate says it could be anywhere from 48% to 53%. Right? And so it could be on either end. It might be less than 50%, which means it wouldn't be a majority. It might be more than 50% because your interval allows for both possibilities. It could be more, it could be less. And so we actually can't answer that question. We would have to say it's unclear whether there's a majority, because it might be less than 50% and it might be more than 50% according to the estimate that we just created. So it is possible that these confidence intervals may not actually allow you to draw a conclusion to some of these questions, right? So it's unclear in this case if a majority of lawsuits are dropped. So those are the three possible outcomes of trying to draw a conclusion from your confidence interval. You might be definitively able to say yes if it's clearly completely above 50% all the way. You might be able to definitively say no if it's completely below 50% all the way. But if it's straddling that number, if it's a little bit below and a little bit above, if 50% is included within that range, you have some estimates that are going to be below 50% and some that are going to be above, then you can't draw a conclusion if it's a majority, right? Unclear if a majority of suits are dropped or dismissed. All right. So this one you'd have to say we can't know. The data is inconclusive on that. All right. So let's take a look at another example. All right, so how about we do this? Let's have you try to construct the confidence interval this time. They didn't give us any background information. They just gave us the numbers that we need to do the calculation. So n is equal to 2,000. So the sample size is 2,000, which is humongous. X is equal to 400. So we have 400 successes out of the 2,000 trials. All right. And we want a 95% confidence interval estimate. So see if you can put that together. Again, it's just a little bit of information, but there's a lot of stuff to do to construct that confidence interval. I'm going to work this out off camera. We're already past the hour mark. This will save us a little time on the length of the video. And then I'll try to do it as organized as I can, but I will resume the recording with the work showing so that you can check to see if you had the right ideas on all the different parts of this problem. And I don't know if I'll be able to fit it all on one screen, but I'll just kind of scroll through it so you can kind of see the work, how it should have looked. I don't know if that's the right way to say it, but let's see if you got the correct numbers that you were supposed to get. So go ahead and pause it. And then once you've worked it out to the extent that you're able to, resume the recording, I'll resume the recording. You resume playing the video and see if you came up with the right answer. Okay, so here's my work. I'll just start with the lowest level. I said I wasn't going to do the dream analogy anymore, so I'll stop saying that. I'll start with alpha though. That's like maybe the first thing you really have to calculate to get all the other stuff to be possible to calculate. So we want a 95% confidence level. So alpha will be 1 minus 0.95, which is 0.05. Now that's calculating alpha, but for the purposes of finding the critical value, you want to divide that alpha by 2. So you get 0.025. That's the area that goes into both tails of the normal distribution. And you want to find the z-score that's associated with that particular area in the left or right tail. So you do inverse norm of that area, which is 0.025. And you should have gotten a critical value, a z-score of negative 1.96 if you use that value. But we're going to drop the negative sign for the critical value, right? So we're going to use just 1.96 as z. And that's from inverse norm. Now that you have z, you can calculate the margin of error, right? So you're going to plug that in for z, 1.96. Stuff in black was already known before I had to find all this stuff, so I already had that stuff plugged in and ready to go. P hat is 400 over 2000, right? That's the sample proportion. Q hat is calculated up here. It's 1 minus P hat. And yes, I know these could be reduced, but if you want to use that trick I talked about with taking that number to the third power, you want these denominators to stay the same. So even though you could reduce these two, and even if these two became the same, it wouldn't match this one. This has to be n, which is going to have to be 2000. So I want to keep these as 2000 as well, even though that makes these numbers kind of big. And then when I type this into my calculator, I had 400 times 1600 over 2000 to the third power. That's what I had inside my square root. When I multiplied all this out, I got a margin of error of 0.0175. Again, if you are close to that, so let's say you went through the problem yourself and you got something really close to this, but maybe it's off, like the 5 was a 6 or an 8 or some other number. That might be attributable to rounding because, again, I feel a little nervous about how much I'm rounding the z-score. I only went 2 decimal places this time, and I don't know if my stat lab is going to find that acceptable. So again, do as I say, not as I do. When you're doing this calculation, the safest thing is to keep all the decimal places for the z-score. So keep them all there. And then if you do, this might not be exactly the thing that you would get. But your answer would be better than mine. Mine's might be off because I rounded a little bit here. So that's the margin of error I come up with. Now that I have the margin of error, I can actually get my answer. I take p hat minus the margin of error. That gives me this lower estimate of 0.182. Again, depending on how much you're rounding in these various places, this might be a little bit different, but it should be very close to 18%. Maybe 18.3, 18.1, but it shouldn't be very far. So if you got like 17 point something, there might be a little bit of an issue there. For the upper estimate, I take p hat plus the margin of error, which gives me 0.218. If you got 0.216 or 0.220 or something like that, that's close enough. That means we're in agreement essentially. And in fact, you probably have the more correct answer because if you got something different, it's probably because you didn't round as much as I did. I hope that's why. Okay, so that would be my 95% confidence interval for the numbers that were given. All right, now that's a lot of work. It's a lot to consider, to learn, to practice. But if you do these problems a few times, you get used to the 4 layers that you have to go through and what order you got to find things in and where things have to get plugged in. And you'll have all these formulas with you when you take the test. So you just got to find the numbers and plug them into these formulas to get the result. Determining sample size. So we're going to be asked to it's not really the reverse of what we've just done, but sometimes you might, like when you collect a sample, you don't know what margin of error you might end up getting, right? You collect a sample and you just kind of arbitrarily pick, I'll have a sample size of 100, right? That's kind of how we've been doing it, right? Let's just kind of make up a sample size and we'll just go with that. Sounds good, right? But then you might get a margin of error that you find unacceptable, right? If you do a sample size of 50, well, you might get a margin of error of like 7%. That's kind of a lot. That gives you a really big range of possible values. You might not be comfortable with that. So one way you can reduce the margin of error is by having a bigger sample size. That's the thing you probably have the most control over here. Because you don't really have a lot of control over p hat and q hat. You don't have control over z. Once the confidence level is determined, z is fixed. But the sample size, that's something you can control. So if you want to, the bigger the sample size is, the smaller this number becomes, the smaller the margin of error will be. And so if we want to reduce the margin of error, we can increase the sample size to do that. But you can even go one step further and you can just decide, instead of like, okay, I'll just go to 100 and see what that does. You don't have to wait and see what that does. You can actually calculate what your margin of error, let me say it this way. You can actually calculate what sample size you would need in order to get the margin of error that you want. So if you know what your acceptable margin of error level is, you can use that to determine what sample size you would need to achieve that margin of error. And so that's the next kind of problem we're going to be doing. And so I'm taking the margin of error formula. I just want to show you that this is the margin of error formula, And I'm not going to go through the details of it. Sometimes I do when I'm in a face-to-face class, because again, it's algebra. This is why algebra is helpful in statistics. You can solve this for n, right? So we can take this formula, get n by itself, and when you do, this is what you get. So when you move all this stuff to the other side of the equation, this is the formula. This is how the formula turns out. So the sample size will equal the critical value squared. Now, it looks like a lot of stuff is going on here, but it's just a z, right? The alpha over 2 is just a subscript. It's not numbers that get plugged in here. It's just a z-score here that gets raised to the second power, right? So we have z to the second power times p hat times q hat divided by e squared, where e is the margin of error. It's your target margin of error. It's the margin of error that you want. The one drawback to this is, in order to calculate the sample size, you would need to first determine the margin of error that you want, but you would also have to have a value for p hat and for q hat. And that's your sample proportion. But think about that, right? You're trying to find the sample size, but in order to do that, you have to know the sample proportion. Well, how can you know that if you haven't even got the sample size yet? Because that means you don't have a sample. How can you know the sample proportion if you haven't collected a sample yet? Because you don't. That's what you're trying to figure out, is what sample size do I need before I collect my sample? So how can I know the sample proportion before I've collected my sample? That's a better way to say it. And it turns out what you're going to do here is you're going to either estimate what this could be based on your knowledge of the situation, based on previous studies that were done on the same topic. You might be able to get an estimate for that. Or if you can't, you'll just use 50% as the worst case scenario. So the biggest sample size you would possibly need is if p hat and q hat are both 50% each. If they're 50-50, that's going to produce the largest sample size that you would possibly need. It'll be smaller if p hat's something different. Like if p hat's 70% and q hat's 30%, that reduces the size of the sample that we would need. Worst case scenario is if it's 50-50. And so if we don't know what p hat and q hat are, I'm sorry, I'm jumbling my words. I'm getting kind of tired. If we don't know what p hat and q hat are, we're just going to use worst case scenario 50-50 and just get the biggest sample size that we would possibly need to get the margin of error that we want. All right. So, and this is what I just explained, right? If you have an estimate for p hat and q hat, use those in this formula. If you don't have an estimate, use 50%, 50%. So that's going to be 0.5 for p hat, 0.5 for q hat, and when you multiply 0.5 times 0.5, you get 0.25. Now, it kind of bugs me that the textbook presents this as a completely different formula. It's just the same formula as this. It's just you're using 0.5 for p hat and q hat. So when it's not available, sorry, I keep forgetting to switch to the pen. When it's not available, you assume p hat and q hat are both 0.5. And plug it into this formula here, and then you end up getting that. So you can either remember it as a separate formula if you want. I feel like it's a little bit silly to do that, but that's kind of how it's being presented in the textbook. Or you can just remember, if I don't know it, I plug in 0.5 for both. All right. Okay, so let's look at a problem. Now this question really makes me laugh. It must be super duper old. I say super duper old, but so much has changed so quickly that some of this stuff feels like it's a long time ago, and it's really not as long ago. I don't know. Again, maybe it's because I'm old. It doesn't seem like it's that long ago, but it's just funny, the wording on this question. And I bet it was like a cutting edge question in like 2000, but now it's 2020, and this question seems really funny, but it's funny we're still using it. And I thought about changing it out because I'm like, oh, this is just kind of embarrassing. It's obviously a really old question, but I decided, I don't know, I just kept it. It's a workable problem, so we'll go ahead and do it. The internet is affecting us all in many different ways. That's still true, but it's so pervasive now. Like, this is at the time when it's just seeping into the culture, So there are many reasons for estimating the proportion of adults who use it, right? What proportion of adults use the internet? Gee, I don't know. I think these days, it's got to be really close to, you really can't get by without using it at some point, right? I mean, I'd be interested to meet somebody who is able to live their life without using the internet for anything. That'd be amazing. I don't think that happens anymore. But there was a time where you had a choice whether you wanted to use the internet for anything or not. And that's kind of the time we're in now with this question. Assume that a manager for eBay wants to determine the current percentage of U.S. adults who now use the internet. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? All right, so there's some numbers there for us to use. We want the margin of error to be no more than 3 percentage points, meaning the worst margin of error that we're willing to accept is 3%, right? So they're calling it percentage points. Don't let that wording throw you off. It's just 3%, which is 0.03, right? So we want the margin of error to be worst case scenario 0.03. And so that's what we're going to set our margin of error equal to. And that way, the sample size we come up with would guarantee that we at least get a margin of error that's 0.03, if not less, right? So we're kind of calculating the worst case, like, again, I keep saying worst case scenario, but we're trying to find what's the largest sample size I would need. Not the largest one. I don't know. What's a good way to word it? We're trying to find the smallest sample size we would need in order for our margin of error to be no more than this 3%. But it's possible once we get the numbers, it might be less, but we want to make sure that it wouldn't be any worse than 3%. I don't know. Hopefully that makes sense like how I'm saying that. So, and that's what this calculation hopefully is going to do for us. It's going to give us a sample size so that if anything, the margin of error might be less than 3%, but it won't be more than 3%. Right. Now, there's parts A and B here. Part A is we have some, knowledge that we can use to estimate p hat and q hat. So we don't have to use 0.5 for those, right? Now, part B is we don't have an estimate. In that case, you use 50-50, which of course is silly to estimate that only 50% of adults are using the internet. But, okay, and I guess this actually dates the question. I said 2000. Maybe I was being a little bit too harsh. So 2006, 73% of adults used the internet. Simpler times, right? So that would be an estimate for p hat. So here we have an estimate. So we should use it. We have some idea of what that number is equal to, so we should use that number. Which means q hat will be 1 minus that, right? Which is going to be 1 minus the 0.73, which is going to equal 0.27, right? So q hat's 0.27. P hat is, and this is for part A, p hat's 0.73. We know E, we want E to be equal to 0.03. Again, so we set E equal to the worst case scenario. I keep using that phrase. I don't know if it's the right way to say it. But we set E equal to the largest margin of error that we're willing to accept in this situation, which is 3%. That's the worst one that we would want. We don't want to be any worse than that. So that's what we set it equal to. And then we want, so something that we have to still find. So, using this formula, I almost did the wrong button there. Either of these formulas, which we're using the top one, by the way. But so what do we have so far? We have p hat, we have q hat, we have E. What we don't have is Z. We don't know what Z is equal to. So I still need to calculate that before I can find the sample size, right? We have p hat, q hat, E. So we need to find Z. In order to find Z, I need to use alpha. Alpha is 1 minus the confidence level, which for this problem was 95%. Wasn't it? Yeah, 95%. Now here's the thing about alpha, about Z. If alpha is the same number, Z will be the same number. So actually, I'm not going to have to recalculate this because we already did this calculation and it's going to be the same thing here. So now this will not be true in 7.2 when we do when we do population means. In that case, even if the alphas are the same in two different problems, the critical value will be different because in that section, we're going to do things a little bit differently. And the critical value we get will depend on the sample size as well. So the only way you're going to get the same critical value is if the alpha is the same and the sample size is the same. And that's rarely ever the case. So even with the same alphas, you might get different critical values in 7.2. But in 7.1, with the normal distribution, with z-scores, same alpha, same critical value. And we already did an alpha of 0.05, right? That's the problem we just did here, back here. So here, we have an alpha of 0.05. We divide that by 2. We do the same thing in the problem we're working on right now. And we put that in the left tail and the right tail. Inverse norm on that area. we're going to get the same value, right? We're doing the same calculation, we're going to get the same number. So it's this all over again. So you actually, for this material, you can actually kind of memorize these. Once you've seen them a few times, you'll just know. Oh, if alpha is 0.05, the critical value is 1.96. If alpha is 0.01, the critical value is 2. I can't remember what it was. I'm a little rusty, but 2.7, whatever, 2.576, right? Isn't that what it was? Right, for this one? Right. The critical value was, 2.576. So if alpha is 0.01, that's your critical value every single time. So once you've seen it a few times, you'll start to pick up on that, and you'll say, oh, I remember this one from that other problem. It's going to be the same thing here, right? And I'm going to take advantage of that here. I've already calculated the critical value for an alpha of 0.05. So instead of redoing this calculation again, I'll just use the result that I got before. So when alpha is 0.05, I was about to redo the calculation, but then I realized I don't have to, right? It's going to be the same z-score that we got before, right? So this will ultimately lead, you're going to do inverse norming. I said I wasn't going to do it. So I'm not going to redo the calculation, undo that. Let's just, I hope it makes, I feel bad not doing it for some reason, but hopefully it makes sense, right? Same alpha, same z-score. It's going to be 1.96 again. And now that I have the z-score, I can find the sample size I need to get a margin of error of 3% or less. Right, it's going to be n equals the z-score squared times p hat q hat over e squared. I just got to plug the numbers in, and I will get my result. So z is the 1.96. That has to get squared. P hat is 0.73. Q hat is 0.27. And we are going to divide that by e squared, which is, I almost wrote an e instead of a 3. That's why I messed that one up. 0.03 to the second power. Right? And we just have to dump those numbers into our calculator, and we'll have a value for n, which of course we should round, but you want to round up. Because if you round down, your margin of error might go a little bit over 3%, right? You want to round it up to make sure that if anything, the margin of error will be less. So if you want to make sure it's going to be a little bit less instead of a little bit more, you want the bigger sample size. So if it's a decimal, round it up to the next whole number to make sure that the margin of error will be less than 3%. So I have 1.96 squared times 0.73 times 0.27 divided by 0.03 squared. And I'm getting 841.3104. And even though that's a 0.3, I'm rounding this up to 842. And so that's the sample size I would want that, given the estimate we have for p hat, should give me a margin of error of 3% or less. 842. So that's how many people I would need to include in my survey to make sure the margin of error is as low as I need it to be. All right, that's part A. I'm sorry, this video is getting a little bit long. I apologize for that. We're almost done. I think I have one more. This is my last example here. And this one's kind of a tricky one because you're trying to work backwards. You have the confidence interval. You want to work backwards to find p hat and the margin of error. And so I'll talk about how to do that in just a second. Okay, but we got to do part B here. So part B is no value is known for the proportion. We have no idea the proportion of adults that are using the internet, right? That's what we're pretending here. So if that's the case for part B, if you don't know, either use the other formula that was listed on that previous screen, or just remember that if we don't know what the number is, we just assume p hat and q hat are both equal to 0.5, right? So either use this formula or just use the same formula we did for part A, but here we're going to plug in 0.5 and 0.5. And that's what I'm going to do. That's the way I think of it. So everything else is the same. E is still 0.03. Z is still 1.96. But for p hat and q hat, we're going to use 0.5 since we didn't know what those values might be. We didn't have any idea, right? So n equals n, I said n again. N equals z, which is 1.96 still, squared. P hat, which is going to be 0.5. Times q hat, which is 0.5. The whole thing divided by e squared, which is going to be 0.03 squared. Like I said, this is worst case scenario. This is going to give us, when you assume p hat's 0.5, it's going to make the sample size the biggest it would have to possibly be to get a margin of error of 3% or less. So this is actually going to be more than 842. That's what we're going to find here. So we'll get 1.96 squared times 0.5 times 0.5 divided by 0.03 squared. And I get, it's quite a bit bigger actually, 1,600 and, not 600, 1,067.11111, right? Which we will round up. You always round this up for the sample size. And so that would be the sample size we would want to have to be sure that our margin of error was less than 3%, at most 3%. Now what could happen, because our estimate was 0.5 and the actual value of p-hat's probably closer, like especially today, like I said, 99%, that we will actually, because it's such a big discrepancy, this margin of error is actually probably going to be a lot less than 3%, given that the actual value of p-hat is probably much higher than 0.5. But again, we're satisfying the criteria. We're making sure the margin of error will be less than 3%. Okay, so that's part B. Now, this last one, I don't usually put this one on the test, but it is kind of interesting that you can work backwards to figure out the point estimate and the margin of error given the confidence interval. So if somebody says, here's my confidence interval, and the fact that it's 95%, I don't think we really need. That's not really going to be part of our calculation. But you might be curious. So if I just gave you my result, you might say, well, I wonder what they got from their sample, because this doesn't tell you. It doesn't say what my sample proportion was. Or you might wonder, well, what was their margin of error? It doesn't say here, right? So, but you can calculate it. So you can work backwards to figure out what that information was that gave me this particular confidence interval. So remember, 0.58, and there's formulas for this, but I'm just going to show you like the logic, the concept behind it. And this is 0.81. Remember how the lower estimate is arrived at, right? This is p-hat minus the margin of error, and that's equal to 0.58. That's how they got that estimate there. This is p-hat plus the margin of error, and we know that's equal to 0.81. That's how they got the upper estimate. And guess what this is? This is a system of equations. This is algebra. This is college algebra again. So how do we solve this system of equations to find the value of these two variables? Well, the quickest way is to notice that this has a minus e, this has a plus e. So if I add those two equations together, the e's cancel out, and then I can solve for p-hat, right? So that's what I'm going to do here. So I'm going to place this equation underneath this one. Let me use a different color here. So we have p-hat plus e is equal to 0.81. So if I add these together, right, the e's will cancel out. So I'm going to get, what's a different color here? 2, because when I add the p-hats together, that's going to be, it's like a variable. It's 2 p-hat. The e's are going to cancel out. And that's going to equal, when I add these two together, 0.58 plus 0.81, which is going to be 1.39. And then I can solve for p-hat by dividing 2 on both sides. Okay? So quite simple. Now the formula that you'll see in the textbook is it tells you add these two numbers together and then divide by 2. But there's no reason to memorize that as a formula or remember it as a formula if you just set it up like this. It's just a simple system of equations. And then that way you don't have to bother with remembering a formula. So here I'm getting 0.695. So that would have been the sample proportion that would have given us this confidence interval. Now I want to find E, so how would I find that? Well, how do you normally do that with a system of equations? Once you find the value of one of your variables, you plug it in to either equation would work, but this one I think will be easier because E is already positive. Plug p-hat, the value of p-hat into this equation, and then you can solve for E, right? So I'm going to have 0.695 plus E equals 0.81. And then all I have to do is subtract that to the other side to solve for E. So minus the 0.695. And that's going to give me my value of E, which is 0.81 minus 0.695, which is going to be 0.115. So that would have been the margin of error that this person calculated, which is a pretty big margin of error, right? It's 11%, 11.5%. That's a pretty big swing. So that's how you calculate the original sample proportion and margin of error. In the textbook, they give you a different formula, which actually doesn't really quite match up very well to this. They tell you to subtract these numbers. Because if you subtract these, when you subtract this one from this one, it'll make this p hat negative, which will cancel out with this positive p hat. But then you distribute the minus sign and it makes this e positive. So you'll have e plus e, which is 2e. So when I subtract these, you subtract these numbers, and when these subtract, you get 2e from that. So you subtract these two numbers, divide by 2, and you'll get the same answer. You can check that if you want to. But you could also just think of this as a system of equations. So that concludes the video on 7.1. Thank you for watching. I'll see you in the next video for 7.2.